Good morning, everyone, and thank you for joining us for our webinar series again. We took some time off over the summer, but we're back now with our regular webinars. So thank you for signing up, and also thank you for joining us today. Today's webinar will be, the subject is how to use nonlinear structural stabilization to aid convergence. And our presenter will be our own Dr. Abid Kiskia. He will be doing the presentation today. He's located in our Columbia, Maryland office. I'm located in our office here in Durham, North Carolina. Today's agenda, I'll give you a quick overview of mallets. We'll have the webinar, and then at the end, we'll have time for questions and discussions. And also note that in the control panel of the GoToWebinar, there's a space there for you to type in questions. If questions come along during the webinar, Dr. Kiskia will be able to see them there. If it's something he feels it needs to answer during it, he will. If not, again, we'll have time at the end for additional questions. Our mission statement is Mallet Technology. We use world-class engineering software tools combined with our broad knowledge and expertise to help our clients compete in today's marketplace and produce reliable and cost-effective products. We've been serving engineering customers for nearly 40 years. Again, we have offices located in Durham, North Carolina, and Columbia, Maryland. We offer ANSYS consulting services in all physics, including structural, fluid dynamics, electromagnetics. We do ANSYS training we can do that at a mallet location or a customer location. We do ANSYS software sales in Maryland, Virginia, North and South Carolina. We've been an ANSYS channel partner since 1985. We have strategic partnerships with Ozen Engineering in Silicon Valley in California, and also with CAD/CAM America in the Detroit area. You can always visit us at www.mallet.com. Like I said, we've restarted our webinar series, and we have upcoming webinars. Our next one is how to use ANSYS space claim scripting to parameterize your models, and that will be next Friday, September 13th, same time, 11 a.m. Eastern. Then next month in October, on the 11th, we're going to do a webinar using overset meshing in ANSYS Fluent, and that will also be at 11 a.m. October 11th. You can register for either of those webinars and future webinars at our website, mallet.com. Again, thank you for signing in. I'm going to turn the meeting over to Dr. Kiskia, and he will start with the presentation. Remember, you can type questions during the presentation or hold them till the end. Thank you.
Hey, thank you, Bas. Can you hear me, Bas?
Yes.
Okay, well, thank you. Thank you very much, Bas, for introduction. Hey, good morning, good afternoon, everybody. Based on your location in the world, I see people checking in here from different parts of the world, and that's encouraging. I like that. So today I'm going to be talking about specifically how to use stabilization in ANSYS structural analysis and shed some light on some experiences that I've had, and in addition to how to use it within ANSYS. And if we have time, we'll share some examples. So initially, start with a little bit of background, just where it is, where can you see instability, methods to handle it in ANSYS, and then we dive into the actual stabilization. It's only one command, but then you can do so much with it. And I have an option to show you two examples. We'll highlight. If we have time, we dive deeper into them. And we'll do a summary and then question and answers if we have time for that. And as Bas said, if you have any question, please put it in the chat window, and then we can look at it at the end. And then I'll open the floor at the end if we have time. I see I've got another 40 minutes or so. I'll talk for maybe 30 minutes and leave about 10 minutes for Q&A. Okay, so where do you see instability, structural instability? Well, it's if you got a structure which has columns in it, has membrane elements, shell elements. You could see it in vacuum tanks. I'm showing some examples here of large columns here which collapsed at some point, maybe under wind or on some heavy loads. We see it in this big tank, local collapse here or local instability in the structure, which eventually collapsed it locally. There's a pipe here with instability causing it to completely buckle and have a different shape. We see it in bottles. This is a good example, which is, by the way, many of my examples are from ANSYS and ANSYS materials. So if you need more information about it, let us know. We'll give you more information. This is a bottle which is crushed here, and over here it's buckling from one shape to another. These problems can be local or can be global. You could have local instability because of maybe local plasticity, or maybe the whole structure will collapse. They are big challenge for us in the consulting world and engineering world when we try to model them. You see them in the form of convergence difficulties in your solver. It just doesn't converge if you go blindly and solve it. And the key is really to predict where is that happening, how, and then tackle it. There are also problems in which you want to ride on the buckling shape, say, or you want to go beyond the collapse, either to understand, what the structure is doing beyond that, and possibly carry more load, carry more simulation as far as you're concerned. And this is a really challenge in terms of modeling. So if we look at just hypothetically here, take an idealized load path for atypical problem. Think of maybe a beam or a column. You're compressing it, and what you will see is the behavior of the structure, which will have to see any form of buckling, some form of imperfection. It follows this dark. This path here, dark solid path, essentially. That is what we would think the structure should follow. It's idealized behavior, what I'm showing you here. However, if you really load it and monitor load deflection, what you will see is you climb on this curve and then you snap possibly to a different position because the structure will take another shape, from one shape to another shape. Now, what we refer to this point as limit load, essentially a term which is used in engineering. This portion is very challenging for modeling. You can't ride on this. It will be very difficult. Some modeling techniques allow you to ride on that, but that's kind of tricky. Another curve which we are interested in is this one, the truly idealized path, which is linear. You will see this if you do, let's say, linear buckling, meaning you look for the eigen value problem. Essentially, look for a critical load, and by doing a structural static analysis followed by stability analysis, or bifurcation analysis, we call it ANSYS, to predict this. And this point, by the way, we call which we can predict in almost linear analysis. We call bifurcation, where the structure can have either shape, can go left or go right, or follows essentially this path of that. So bifurcation, by definition, is where your structure can have two or possibly even more sometimes form of deformed shapes. What exactly happening here? Well, we need to tackle this problem in ANSYS. So one way to do it is which we done in the old days, is we follow the first method. Is we predict, we use this method here. We just do linear analysis, static analysis, and then we look for what form, what shape the structure will take as it bifurcates. You can predict this force by doing what ANSYS called perturbation method, or it's got some form of eigenvalue solution. which gives you a critical load. That's extremely conservative because the load predicted is really high. Another way is called load control or arc length method. This is a modified Newton-Raphson, where you do large deflection analyses and you try to follow this curve, which is really tough. That's a challenge here in terms of analysis. That's another method for tackling instability in structures. A third one is you convert your problem, make it displacement control. So instead of load control, displacement control, and these are easier because they tend to be stable, but not every problem can be converted to displacement control to see what's a critical load for it. The method which I want to focus on allows you literally to predict this shape here nicely. You know, essentially jump from the limit load to another form, and that's what we call in ANSYS nonlinear stabilization. So that's my focus today. And what exactly are we doing here? Let's see what happened to my slide here. Okay. Think of it this way. Okay, I want to have a structure here and show you how we physically solve a problem. Just imagine we adding what you do. The solver adds artificial dampers, adds dampers to every degree freedom, every node. And so if I'm here at this location and I notice instabilities in the structure, which you can see during solution, you activate that method. So ideally, and that's very ideal because you're adding artificial energy to the system. Yeah, the solver adding extra forces, damping forces, which are relative to what we might call pseudo velocity. Okay, every node, every degree freedom will have a dashboard attached to it to control its motion. Okay, and again, we talk about here nonlinear static analysis. So where does damping come from? Well, it's calculated by the code because you know the delta t, which is the integration time step for the solver, and then you have the displacement, divide one by the other, and you get a pseudo velocity. And then the amount of displacement, if it's large or small, you're going to have large or small force resisting that shape that structure like to take as it buckles, as it goes from stable position to unstable position. So essentially, so what's exactly specifically happening is when you, I'm pointing this point. Let's take, for example, this arch, and we're applying a load to it here. This shape is A, okay? We're gonna jump from this state, essentially, to another stable state here. So displacement at this location will be very large, okay? Meaning because it's unstable. Yeah, structure is unstable. Large displacement will cause large forces because the displacement will be large, and hence I can apply this artificial damping in a controlled fashion with large quantities if the instability is large, and if it's small, then it will be small. However, one has to be careful how much of it to apply. Okay, otherwise you go and you either you predict the wrong shape, or it will go nowhere. It will just stop. Yeah, you get a solution which is the wrong solution. So again, let me summarize here, just a bit of summary points here. Large displacement are indicative of instability, as opposed to small displacement predicted by the solver. For that to happen, that's what buckle shape means, and I want to resist that behavior through applying the damping forces, resistive damping forces, in order to go from one shape to the other. Now, again, let me repeat a few points here. This is, I want to say, it's artificial, so we have to control it, and it's activated by user control. I will show you that shortly, and then I need to how much of it I have. So we talk about physical number, which is damping, has the same units as the actual damping we have. However, we know it's artificial as such. The damping force that's used in the code is proportional to what we call damping factor. Damping factor, we will be able to control it within the ANSYS command used to activate this feature. Okay, so how do you use that in ANSYS? There are two forms. of when you define it. Okay, two methods for definition, I would say, but effectively, you get two methods also in controlling the solver behavior. One is what we call energy, and the other we call damping. Just ignore the terminology. Both apply damping inside the code. The energy method, you specify a value within ANSYS, which is a ratio of the energy dissipation at step one. Once you start activating the feature, you are actually applying artificial energy in the code, okay, resulting from the stabilizing forces. That ratio of that energy you're applying to the actual energy is called, we call it damping factor, energy dissipation ratio. That you control. So you specify that, and then the program from internally, it will calculate what's called factor. The factor I talked about in the slide before. The factor controlling the definition of this force. Okay? So, what does that mean? That means I might end up with different values at different locations. So the factor will vary from one element to other. Why? Because the energy is different, yeah? If you have at different elements, if you have an element going through some kind of local instability, or the displacement in that element are large, is going to have more energy, and hence the factor there will be bigger. This is really nice where for local, if you have local instability, like local plasticity, what have you, that's good to use this method. The other method is you define the factor itself for the whole structure. You say what's the damping factor, and you specify it by activating your activity. So you want to activate damping and the damping factor. So think of it as a damping coefficient of some sort, which is the same applies to. So if you have a structure, a system in which you get a complete collapse and global instability in it, you know, a column collapsing, a membrane, big membrane type structure collapsing, that you probably want to use. Now, if you know, and most probably when you do nonlinear analysis, you will start to get knowledge in this area. You know what kind of damping you use in the system. There's some defaults you can run on, but what I recommend to you soon we'll start doing, it's trial and error and building experience. So this is very challenging. Low applications, you might also apply both methods. Okay, you probably start with energy method because it's localized and it's different parts of the structure, and switch to global method through some kind of restart analysis, that's what we recommend to do. Now, how does it work inside? Okay, the two ways for it. One is you apply in the code. One you apply once you activate, it stays constant. So you apply it at maybe load step one, which is very and likely you apply it throughout the load. So you solve the problem, and you this instability, you go back and you do some kind of restart. You can activate stabilization as a constant number, will stay constant through the whole load step. Okay, that you're solving, or you can do it in a reduced fashion, meaning you want to start a number and then drop it. Okay, so at the end of the load step, it goes to zero. So just in summary here, two methods. You can have it constant through the load step, or start at a value and drop it down to zero. They're really problem dependent. The key here is the artificial energy you're applying to be known to you and see what it is, and then most likely we'll go back and forth between different solutions to quantify the results that you have and qualify them. In many applications, and the one I show you, constant value is not bad. However, one thing you want to watch for is don't in any linear analysis, you cannot allow things to happen instantly. Okay, you might encounter difficulties if you apply it suddenly, immediately, or you take it away. Okay, so you got to be careful with that. If that's the case, then you probably want to go back to the method which is reduced method. So ideally, in any application, in fact, for all linear analysis, when you apply loads or you apply features in an instant fashion, it causes instability in the solver and things go haywire. Okay, so how do we apply it? We said either constant or either linear dropping down to 0. But within the load step, I have 4 options. So to find my loads, and by the way, I'm talking using ANSYS language here, assuming that everybody is an ANSYS user, or at least if you're not, you're familiar with it, and that the terminology is assumed here. I have within the load step. How does it work? Okay. Well, by default, it's off. There's no stabilization. The command is not working. It will not be working because you don't want it. Yeah, you don't want this working for every problem there is. So the default is off. The second option is you want it to turn on once you have non-convergence. Say, and that's option. This is on non-convergence, meaning that within the load step, the program is going to try to solve and keep bisecting till it hits the lowest delta T, and that's basically what says it's not converging. It will activate at that moment. That's option 2. And option 3, I don't know if I said 4, but option 3 is you want it active at the beginning, regardless, at the beginning of the load step. Okay, so they're based on the problem you have. You might basically switch between these two. And the examples I show you, it will really make a difference where you activate it. And that again, it's because you're applying artificial energy, you're applying forces here, so you need to be careful when you're applying and how much of it is being applied. In most well-posed problems that you define very nicely, no stabilization is at the beginning. You really don't want it because you don't know how much of it to apply anyway, unless you've known the structure and you're really doing some serious analysis and everything is in control. I found that most of the time you'll be doing some solution followed by a restart. Okay, so you will assume you solve a problem and you notice instability somewhere halfway, somewhere maybe 20% the load, 30% the load, and you must save the restart files for every point. Then you want to go back and do restart, activating the stabilize command and see how the solution goes. Okay, so when we apply it as it's the program solving, you are talking about some forces. That's what's called stabilization force to control the motion of the structure and the various degrees of freedom. We want to make sure that these forces are under control in terms of the value. How much of it can you allow and accept, and your solution is still acceptable? Well, that's controlled by what we call stabilization force limit. 20% of the L2 norm. What is that? Well, L2 norm is a measure we use in the analysis. So I look at we look at. Hello, Baz?
Yeah, I can hear you.
Hello? Hello?
Abby, we can hear you.
Yeah, we
Can
can
you hear
still
me?
hear you, Abby.
Oh, sorry.
Yeah, something happened, but go right ahead.
Can you hear me?
Yes.
Okay, sorry about that. There was some crisscrossing communication here. My apologies for this technology. It's too many phones around me here. L2 norm is a measure we use for calculating forces. You want to make sure that the L2 norm for those stabilization forces is less than the L2 norm of the internal forces in the systems. 20% is a magic number, but you probably want it to be smaller than that. More than that, then it would be applying too much external energy, and that's not good. Okay, so and the program will give you warning if it's too much. You will see warning in the output file. Okay, another way to measure for quality is check energy. We're talking about stabilization energy being applied by these dampers. Well, I can calculate. The program actually will give you it as part of the post processor. Make sure that energy is less than 10%, 5% of the overall energy. From my experience, I noticed that I like to control it locally. If the problem is locally, you probably want to be looking at stabilization energy at a local part of the problem, meaning a local part, a local zone. Don't bother checking the whole system, okay, because that will become too much. And sometimes for certain applications, you really want to control local instability. And I'm talking about overall system, massively complex system in which you mix all kind of elements and element types. Reaction forces at the end can be checked, by the way. So don't rely on the code for warning you during solution. You can actually request output, and this is the old-fashioned output forces will output file. It will really list the forces for you, and you can compare those forces inside those dashboards to the forces, to the noodle forces in the actual problem, or the reactions for that matter, and make sure these are small, meaning small, really small. Okay, so. This is in a nutshell where and how, okay? Now, what exactly, I want to show you that in an example, just to point at the commands themselves. Look at this problem. I chose two applications, two simple applications, by the way. One is a frame type structure where I want to play the animation here. Oh, come on, play slowly. Oops. Yeah, it's going to play. I promise you it will play. Okay, let me go here. Do you see the animation playing? Yeah, please. My apologies for this quick animation. Notice that this frame, what it did, it went. But we have just 2D frame, maybe beam type structure. Applied load here. At some point, you want to know what's critical. At which load this structure is going to snap completely the other way, and you can see that this whole thing just literally flip. It's like the arch problem. And we could do that. However, the best way to solve this problem is by using nonlinear stabilization. I will show you the setup in ANSYS to do this particular problem. Again, let's play the animation just again, and please pay attention to it as it snaps. Look at that. See that? See how it goes slowly? Well, because the solution we saved. But snapping to this, that's a very challenging application in ANSYS. The next problem is an insertion problem. Look at that. I have the insertion, by the way, and the pull playing at the same time because I have two independent problems of let's say, a pin, a connector of some sort inside the socket. And if you try to pull this, I'm going to play it again. Okay. At some point, the solver will stop. You cannot go anywhere. It just the contact between the pin here and the housing is just so there's so many forces here, and you cannot track this at all. It won't go anywhere, and this becomes unstable in terms of solution. So we'll go back and look at the what exactly ANSYS is doing there. Activate the nonlinear stabilization with at a local level and solve. Okay. So let me basically bring ANSYS back again here. So I'm done with these slides, but maybe before I'm done with these slides, let me tell you a bit of a summary, which I'm going to come back to this because I notice I have a little bit of time here. Instability, you see it in many systems, nonlinear systems. They're really challenging, as I mentioned earlier. I want to apply external energy in a nonlinear system and then monitor how much of that I'm applying, so my solution will be worth looking at. And that will be done by, let's go back and look at ANSYS. Can you see my screen here, everybody? Still? Hopefully.
Yes.
Okay, Buzz. Yeah, let me look at the first one. And this is so I want to launch ANSYS. It's going to take a minute. Do you have any question in the chat, Baz?
Yeah, there's one question. Can you see it in the question pane?
I gotta open the pane.
Yeah, there's a question pane and a chat pane. This is in the question pane.
Yeah, I opened the question pane. Show answered questions, but applied. You want to read it to me? Let me start. I'm starting ANSYS here. Just show you that. Let me show this and I'll refer to the question. Let's make it informal here.
Okay.
This is the application we showed you guys earlier. Apply the load. If you look at the geometry here, apply the load here. Let's see, the whole structure static. This is the application, and we get a frame, 2D, apply a load here, increase the load, at some point the solver just stops. And you can see it here if you animate that. See this? That's it. Stops here exactly at this point. Stop, stop, stop. And beyond that, then it goes nonlinear. And what happens? You go back and look at the output file, and you'll see, and then you can the forces. I'm sorry, I'm going to go fast here just to show you that it did not converge, yeah, and tell you there's a start. So what do? Well, I look at the convergence history for this particular problem, and we can see at some point here the code was struggling. Yeah, you see time here is delta t is very, very small here. It doesn't converge. Now, what to do? Well, we said activate stabilization. If I look at this deformation and say I want to take the last point and blindly, as a user, just go back and say, okay, go back, activate stabilization, which you see here. Let's look at that. Nonlinear controls. Stabilization is off. We activate that. If I activate it blindly, I say constant, and go back and say solve. Without regard, let's say from the last step, if you do that, it will not converge. It will not converge because you're taking the last restart file and taking the. By the way, I didn't. I lost my. Yeah, I want to do restart manually from the last step here. If you do that, if you take this and it says solve blindly like that, it will not converge because it's starting with large forces. It just calculates at the beginning large forces, damping forces. So what do? And you can see here, it didn't converge. Again, we have the same challenge. So one way to tackle this is you go back and say, I don't want to restart. If I look at the solution here back again, I want to look at the solution. I want to restart somewhere here, okay? And why is that? Because I have, I can calculate the initial initial force factors better this way here, and I have them, okay? And they will be more manageable because the system is stable at that point, okay? And if I do that, let's say, for example, I will go back and look at the output file, and this is something I encourage every user to do that, is you look at the output, and somewhere you see, somewhere here, okay, roughly, okay? And I did track it, believe me, when I prepared my notes here. If you look at this, somewhere, just before you start doing bisection, I cannot show it because this is the output for the previous one, at step about 32 or something like that. So if I go back and start my nonlinear analyses here, no, I'm sorry, at the previous step, let's say I'll go 18. So just push it a bit deeper before at that point the first bisection started with the code. That's where the instability started in the system. And I say solve, okay, that problem is manageable, and you'll be able to get a better control, a better solution, okay? And we can see it's already stable, and the warning I talked about is shown here. You see that the stabilization forces are large, meaning we have to go and check them. So the solver is going to work and all the way to the end to snap to the different position, which I showed you earlier. Okay, so if we look at animation here of our solution, you can see it snapping to the different position. And let me slow it down so you can all look at it here. See that? Yeah. One thing will be interesting here is you say, I want to look at, I want to animate, I'm sorry, come on, sister. I want to animate just these guys. Okay, 20 frames, take the actual frames and animate only these guys. We'll show you exactly the snap. See that? So this is the restart analysis. You really want to control the damping energy. And now one thing I've done in this problem also is I highly recommend users to do that. Let me stop this here because I'm out of time. I get more questions from you guys. Is where is the output? Where are the output forces? Output forces, you see them listed here. So as the energy at some point. But output forces will be listed, but you need to ask for them. Okay? They will be listed here. You can compare the forces from those dashboards we added to the actual forces in the system. And that you will add, for that, you add command snippet or command object here that request those solutions to be printed. Essentially what you do, you insert out BR and load. You insert a command object here, and that command object will say the following. We'll say out PR, comma, enload, comma, let's say last. So essentially what you're asking for the system to print for you the forces for the last substep, for the last convert substep, or the last substep period that you have in the solution. And I have those, by the way, for you in this particular cell here. So let me go back here and do this. I'll promise to show you that, and I have about 4 minutes of talking, then leave 5 minutes for questions, for answers. How many chat questions you have, Buzz?
We've got one.
I'm sorry, just one?
Yes.
You want to repeat it for me?
Sure. You ready now?
Yeah, while it's launching, I want to show people where the output is because I promised to show them that. Tell me where that is.
The question reads, how much will the results be influenced if the stabilization is still constant at the end of the simulation? For example, if stabilization is needed only locally but applied to all elements.
I'm sorry, 1 second. Let me. I'm launching ANSYS here. So 1 second. I will address this. Is actually a good question because I really want to show people without, because this is important. You really want to know how much energy applied. So I'll keep the screen. This one had in it the command. You see the command here is active, and I solved this problem. This is the command, and it's going to show you in the output. Will show you the following. This is very important. Many young users probably don't know that. Look at the output, and I can see here, you see a list of forces that applied artificially to stabilize the problem. And it's really important that we actually compare. I want to show you just one particular node. Look at this, for example, here. You see stabilization force at this node 15. Yeah, look at that force and the static force. You see here, if I take this guy, you get really small, relatively small forces, e to the -2, e to the -4, compared to the actual forces, which are 10, 400, or 378, what have you. This output is not available graphically, however, I will output file, and you need to ask for it by inserting this command object. Okay? So anyway, hey Buzz, I need to let me take this question because I really like to answer a question and give people time to at least we show them one application. The other application is will follow the same path. So go ahead, Buzz. Repeat the question to me. I'm sorry.
Yeah, that's fine. How much will the results be influenced if stabilization is still constant at the end of the simulation? For example, if stabilization is needed only locally, but applied to all elements.
Well, if it's constant and applied to all elements, you need to be careful. You got to check energy. It is good idea to check energy and make sure the strain energy in the system is way, way bigger than the artificial energy is added. 5%. I like to use this ratio, 5%, and the energy is available as an output. And if I can activate my other system just to show you where the energy is shown, and you can allude to that. Now, if it's too large, what you do, go back and start changing the value of the force factor, how much you're applying, and possibly go back and maybe do reduce method. But if it's too high, then it's not wise to. The answers become questionable, and you might end up buckling or producing the wrong solution. From our experience, and unfortunately, I cannot share a lot of application because of my customer applications. We have mixture. We will mix solid elements and membrane and shell elements, and we have local instabilities from the shells and membranes. And we apply. You know that these membranes will take more stabilization. They will need more energy. So you go back and check it locally, okay? But at the same time, it's a good idea to check it globally. But you want to justify your answers. That's the bottom line. And we really talk about here nonlinear analysis, where engineering judgment is very, very important. And you're applying, essentially, just think of it this way: you're holding the system. You add superficial energy to make sure it carries its shape from one shape. It carries itself from one shape to the other. And the solution has to make sense. And we're giving you a measure here, one to measure energy, another one to measure forces. So you measure the energy. Again, let me repeat myself because I'm not talking about too many things. Measure the energy locally on the part level, and measure energy globally, and justify both. Okay. Hopefully I didn't confuse you with too much detail here with my answer, but that's what I will do. That's what I did in my own consulting projects. Okay. So Baz, if there are no other chat questions, I want to just bring the other screen here,
Okay.
and bring the pull force just to show people how we check that energy. In the meanwhile, take other questions. If anybody want to ask question, we will open the floor in a minute for people. It's launching I just don't want to load the system with too many cells here running. Maybe you can open the floor for questions. Just make it informal, and let people talk if they want to. Can they raise their hands? Baz?
Yes, you can also, I'll make it so you can unmute yourself if you'd like to ask a question. And of course, you can raise your hand also. Or again, type it in the question pane.
Okay. Yeah, go ahead. I just open it. I'll promise people. I make it here informal. I promise people to show them in this system. This is the energy again for that application. The pull force. You see the pull force for that. Look at the application of the energy in this one. We applied the constant. However, more of it was applied locally, certainly because of the amount of local deformation. So constant, and we use energy method. So it will be more of it at this location. And if I look at the stabilization energy, these are the values. So we talk about, once you activate it here, e to the minus, let's say 2.5, e to the minus 4, as opposed to, compare it to strain energy in the system, which literally, they're both going to drop to zero because eventually they'll both be very, very small here. So this number here, e to the minus, let's say 8, e to the minus 3 at the beginning. So it's a good ratio between both of them. But ultimately, the stabilization energy, although you think it's a big number, this is really small, compared to the actual energy in the system. But it's very important that these two numbers get compared. Again, stabilization energy and strain energy in the system, and you compare both and make a judgment on the model. Okay, and then you can also look again, as I said earlier, the output forces, which we're asking for them here. Okay, so these ought to be small. Now you will wonder where these forces are coming from. Well, this is the output file. They are the forces inside those dashboards. This is too big. I'm sorry. Come on, system. Oh, yeah. See, this is the forces listed for you. You basically see the static force on the node along with stabilization force on the same node. So if I look at node here, 17, for example, just pick this node. You have e to the minus 21, e to the minus 7. Compare that to e to the minus 3, e to the minus 4. Certainly, the stabilization forces are small, and hence the solution numerically is acceptable. Okay? Okay, Baz. I see 18 people there. Let's see if I have any more questions.
Yeah,
open the floor for questions.
Unmute yourself and ask a question. You can do that now.
And also tell people we have our email, that this event is also available for people to look at, maybe late this afternoon. If you have any questions of Mallet and about what we do and something specific, maybe I didn't clarify it very well, send me an email. We'll shoot you back an answer. Make sure you're within our region and our domain where we provide services. Mallet, we're focused on the eastern shore, the eastern part of the United States, but our services are provided to all our customers in the United States, North America, and even some global presence as well for our affiliate companies. Okay. I think, Baz, we promised people 45 minutes. If nobody asking more questions or any questions.
If nobody has any more questions, thank you everyone for coming to the webinar today. Again, we'll have our next one next Friday. Please go to our website at mallet.com to sign up. Like Abid said, also on our website, there'll be links put up to this webinar and also all our past webinars if you want to give a listen to any of those. Again, thank you everyone and have a nice weekend.
Thanks, Bud. Thank you, everybody.
Let me make sure we stop.